Assalamu alaikum. Welcome to lecture 2 of chapter 9 on engineering alloys. As usual, we will quickly review what we covered in lecture 1, and today we will continue with the binary eutectic alloy system that we started last time. Right, and that is what we are doing, and in that we will do hypo-eutectoid plain carbon steel. We will try to do some examples on it. Then we will cover hyper-eutectoid plain carbon steel and again do some examples on it. So let us see what you did last time in lecture 1 of chapter. We introduced the iron carbon system to you, the iron carbide phase diagram, the solid phases in the iron carbide phase diagram: ferrite, austenite, cementite, delta ferrite. We showed you this whole diagram, which is the basis of the iron carbide system, the phase diagram, and explained it to you in a lot of. We showed you the invariant points, the peritectic reaction, the eutectic reaction, and the eutectoid reaction, the triple points on the iron carbide diagram. We further described the diagram again to you in more detail. Then we talked of slow cooling of plain carbon steel. You know by now, slow cooling means homogeneous cooling. And with that, we started eutectoid plain carbon steel, exactly 0.8% carbon steel, and what happens and so on when you do homogeneous cooling. So we explained to you exactly at 0.8% the changes that happen when you cool it down. What is perlite? How does it look? And then again, right, the interactive way we have of explaining things and so on. So the same topic we covered once again, but more interactively so that you could understand. We did an example, finding the weight percent of the eutectoid ferrite and finding the weight percent of eutectoid cementite. And we explained it to you on the graph here. We did the calculations, we drew the tie line. We explained how the tie line for this one works, just above the temperature, just below the temperature, and we showed you the final results. We just started this slide, but we told you that now this is a new topic and we will cover it next time. So here we are in lecture 2. So let us now talk about hypo-eutectoid plain carbon steel. Now, if you were in the class, I would generally ask questions and so on, and you would respond, and it would be more lively. Forget about material science and physics and this and that. In your normal English, the words hypo, hyper, super, what do they mean? Right? They have a general trend. I mean, you have a market, you go, it is a bakala, a souk, and so on. You have a market, and then this is a supermarket, and now it is a hypermarket, right? So these words are there in normal English also, and they mean something. So there is something, this is the normal something. Generally in science, here in material science, when we say hypo, we mean less than something, and hyper means more than something, right? So if we are saying that this is normal, then hypo would be below the normal and hyper will be above the normal. So hypo-eutectoid plain carbon steel, eutectoid, you remember, eutectoid was 0.8% carbon. So hypo would mean that any carbon percentage is less than 0.8, then it is a hypo-eutectoid steel. Plain carbon steel, of course, right, if you remember, that we are not adding any other metals or materials. It is just iron and carbon. So it is called plain carbon steel. If we add other things, manganese, chromium, this, that, then this will be not a plain carbon steel. So plain carbon steel is all we are studying for now. It is just iron carbon. And hypo-eutectoid means that the percentage of carbon is less than 0.8. So let us go to the next slide on the next page where the figure is there, and it will be explained in a much better way there.
You see, where is eutectoid steel? 0.8% carbon. 0.8% carbon. What is hyper eutectoid? Any temperature above this. Any temperature above this. Hyper there and eutectoid here. But if you go on the composition line, this is 0.8%. 0.8%. If the composition is less than 0.8, we call it hypoeutectoid. If the composition is more than 0.8%, we call it hypereutectoid. So you see, the hypo and the hyper are about the composition of the steel. If the composition is 0.3%, 0.4%, 0.5%, any carbon percentage less than 0.8, then all this steel is hypoeutectoid steel. And if the composition is 0.9, 1, 2, 3% carbon, any carbon percentage more than 0.8% carbon, then that steel will be called hypereutectoid steel. So hypoeutectoid steel, hypereutectoid steel are compositions, and according to the temperature above 723 is pro-eutectoid, and after that it is eutectoid. So hypoeutectoid steel here, hypereutectoid steel here, and pro-eutectoid temperature there. So this time we are here anywhere. We are here anywhere, right? As an example, they are taking 0.4% carbon. So of course 0.4% carbon is hypoeutectoid, right? Hypoeutectoid. And as usual, you draw a vertical line. You draw a vertical line, and then you see that as we cool it, what will happen? So you know that all this region is austenite gamma. You see this line to this line, everywhere here is gamma. If you go very, very high temperature, 15, 1600, then it will be liquid. But 900, 1000, 1100, it is all gamma. So when you take a hypoeutectoid steel of 0.4% carbon, you go there. At point A, first question, what are the phases present? Only one phase, gamma austenite. Composition of the phase, same as before. Weight percent, mass fraction of the phase, 100%. Once you touch this line, you see this line is the gamma, that line is the alpha. So in between here and here, it will be gamma and alpha, right? Gamma and alpha. So as soon as you are below this line, some of the gamma has transferred into alpha. So here you see you have the circle, you have a few grains. Now whenever a new phase forms, the weakest part we told you is the boundary, right? It is the boundary, right? Grain boundary. So the new phase will start to form on the grain boundary. So alpha here, alpha here, alpha here, alpha here. You will show a little bit of alpha on the grain boundaries. This was pure alpha at A. Once you are just below the point B, then some of the, so alpha, alpha, so this is your diagram, right? When you go below, but above this line at C, then there is much more alpha, right? So those alphas have grown into very, very thick lines. So all these very thick lines, they are alpha, and the rest is still gamma. The rest is still gamma because all the gamma has not transferred. Some of the gamma has transformed into alpha. Here it was very little. Here it is a large amount, but a lot of the alpha. So this is all alpha. This is all alpha, right? Now very correctly, this alpha or this alpha is not alpha. It is pro-eutectoid alpha because it is the alpha formed above 723, right? So here, at any point, whatever alpha you show in your diagram, this is the pro-eutectoid alpha. Once you hit point the 723 Celsius or just below it, as soon as you hit it, whatever gamma was remaining will change into alpha plus cementite, which is the perlite, right? So this will remain. The pro-eutectoid alpha is remain. Whatever rest is there, dash, 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 you convert into the other one, which is perlite. So this one and this one and this one will all become perlite now. So that is what we are showing. You are showing the pro-eutectoid alpha, and you are showing the eutectoid alpha and the eutectoid cementite, and together they are the perlite, right? So whatever phase forms above this temperature is the pro-eutectoid, and here for this example, at A it is all gamma, at B or C it is gamma plus alpha. So this alpha which has formed is the pro-eutectoid alpha, and once you hit the temperature of 723, all the remaining gamma changes into perlite, and perlite is alpha plus cementite. So this is pro-eutectoid alpha, pro-eutectoid ferrite. Oh, sorry, this is eutectoid alpha, eutectoid. It has formed after this temperature. So eutectoid alpha and eutectoid cementite, right? So this is an example. This is an example of a hypo-eutectoid steel. Hypo. I could have taken 0.1% carbon, 0.2%, 0.3, 0.4, 0.5, 0.6, any carbon example, where the percentage is carbon is less than 0.8%. Then any steel here is hypo-eutectoid steel. So whether it is here or here or here, it will behave in the same way, that at a higher temperature of 900, 1000 and so on, it is all gamma. At these temperatures, 800, 750 and so on, it is gamma plus alpha. And at any temperature below 723, it is alpha plus perlite. And this alpha is the pro-eutectoid alpha or the pro-eutectoid ferrite, and this perlite is the eutectoid ferrite and the eutectoid cementite, right? So now you can do any calculations also applying the lever rule at any place, or you can, right? So at any given composition, at any given temperature, what are the phases present? What are the compositions of the phases? What are the mass fractions of the phases, and what is the structure like, right? So these are the only 4 questions. I cannot ask you any other question on a phase diagram problem. So let's proceed. Now if you see under a microscope, we showed you earlier how does a perlite look like, but this time there is some pro-eutectoid alpha, and then there is the perlite, right? So inside the perlite, there is eutectoid alpha and eutectoid cementite. So earlier we had the light gray background and the dark gray lines. Here this time it is like very light gray and dark gray, very light gray and dark gray, and this is how the things look. If you have a combination of pro-eutectoid alpha and eutectoid perlite, right? So for hypo-eutectoid steels, this is how it will be. This is how it will be. If you go inside the dark region anywhere, you see this light one is the pro-eutectoid alpha, but the dark one is the simple perlite. So if you enlarge it further, you will see that this is the same. You have the light background and the dark lines, just like perlite, right? The plain one is the pro-eutectoid alpha, but all the dark one is the perlite. Perlite looks the same as it looked earlier. So if you enlarge it further, you will see the same perlite. In the dark regions, you will see the same perlite as before. So this is the micrograph of hypo-eutectoid steel at room temperature.